Welcome to section 5.3. In this section, we're going to look at more consequences of prime numbers and some interesting just things that can happen with numbers, ways that we can define them. And so the first part of your homework that covers problems really 1 through 9, your homework is 20 questions long, so about half of it deals with this definition of either perfect, deficient, or abundant numbers. And so in order to define those, I put three definitions up here that you can find in your book. The proper divisors for a natural number include all the divisors of the number except the number itself. So for example, the proper divisors of 12. 12 is divisible by 1, 2, 3, 4, and 6. Now it's also divisible by 12, but we don't include that number itself. And so if we think about a natural number, the natural number is like a counting number, so anything that starts at 1 and goes up. A natural number is said to be perfect if it's equal to the sum of its proper divisors. So let's look at some examples here of what we mean by perfect. So if I get a pen going here, if I try to model a perfect number, let's take a look at a potential perfect number. Let's take a look at something like 6. The proper divisors of 6, so 6's proper divisors, are all the numbers that go into it except 6 itself. So we know 1 goes into it, 2 goes into it, and 3 goes into it. Okay, so those are the only three. And so we check whether a number is perfect by adding those up. And if we add 1 plus 2 plus 3, look what we get. We get 6. 6 is a perfect number because it's the sum of its proper divisors. So another perfect number is something like 28, right? 28 is a perfect divisor. Now, I don't have these memorized at all, but they're going to ask you to check whether some things are perfect divisors or not. So if we take a look at 28, trying to get that to go down, but it's not going to. 28's proper divisors, and we'll be methodical. 1 definitely goes into it, 2 goes into it, 3 doesn't, 4 does, 5 doesn't, 6 doesn't, 7 does, right? 7 times 4 is 28. And then we can just start matching things up. 2 times 14. And I think that might be it. So let's look at what the sum of 1 plus 2 plus 4 plus 7 plus 14 is. Well, if we start chunking it together, 3 and 7 is 10. Now we're up to 24, 28. Absolutely, it's perfect. Okay, so we got a perfect one there. So this one that I'm trying to move down is one that was, interesting, is one that is in the homework that I wanted to rely upon when we talk about perfect numbers. Now let me go back up to a definition. So I think you have an idea of a perfect number. Let's take a look at the next definition. So one piece of advice that I have is as they work examples or do homework problems in the textbook, have you do them. They want you to build up a knowledge. So we should walk out of this knowing that 6 and 28 are two perfect numbers. The other definition that's here is of an abundant or a deficient number. A natural number is deficient if it's greater than the sum of its proper divisors, right? So, and it's abundant if it's less than the sum of its proper divisors. So you can come with notes as you come to the test and just rely upon those. So in that homework that I mentioned from 1 to 9, the question that they want to know is, one question was, is 26 abundant or deficient? So let's talk about 26. Let's see what its proper divisors are. 1 goes into it, 2 goes into it, 3 doesn't, 4 doesn't. And I think, as we try to get into there, we're going to realize it's just 1, 2, and 13, right? If we look at 26, it breaks down into 2 times 13. Those are two prime numbers. Those are its proper divisors. So 1 plus 2 plus 13 is 16. Now 16 is less than the desired number 26. So if we go back up to our definition, it's deficient if it's greater than the sum of its proper divisors. 26 is greater than the sum of its proper divisors, so it is deficient. So those numbers adding up left us short. It was deficient. Another problem that they asked was, is 88 abundant or deficient? And so it should be really quick to go through here, although if they pick big numbers, it's not going to be quick because you got to think about all those divisors, which could be an issue. So let's take a look at 88, a little bit harder. 1 definitely goes into it. 2 goes into there 44 times, so maybe it'd be wise to get their pairs. 8 and 8, 16, so 3 doesn't go into it, but we know 4 does, 22 times. 5 doesn't. 6, I'm not so sure, right? Well, 6 can't because 3 didn't go into it. 7, we'd have to check. 7 goes into 8 one time, doesn't go into 18, so 7 doesn't work. 8 we know does, 11 times, and now we're really close. Probably won't pick up anything else. 9 we know doesn't, and 10 we know doesn't, and now we've looped ourselves. So the only thing that we didn't write in terms of its pair is the 1 times 88, because we don't take the proper divisors are the ones that are not the number itself. So let's add these guys up. What's 1? And so we can grab a calculator, right? We don't have to do this all by hand. So we're taking 1 plus 2 plus 4 plus 8 plus 11 plus 22 plus 44. And so if we do that, 1 plus 2 plus 4 plus 8 plus 11 plus 22 44, we get a nice 92. Now, 92 is greater than 88. But the question is that abundant? So if the sum of the digits is bigger than the number itself, then it's abundant, right? So if it's abundant if it is less than the sum of its proper divisors. The number is less than. But maybe it would be better. It's abundant because that sum is bigger than what we were dealing with. It's deficient because that number is smaller than what we were dealing with. So this is abundant. Now it's possible for a number not to be deficient or abundant. What do we call that number? We call it perfect. All perfect numbers, right? The sums are not greater than or less than, they're actually equal to. So I think there's some good true-false questions in there. So one that I found that might take some time, I looked at it and thought, oh, that might take a little bit of time in order to solve. So I thought I'd grab it and we could look at it together. And that's this one right here. The first and third perfect numbers both end in the digit 6, and the second and fourth perfect numbers both end in the digits 28. Choose the correct answer below. And so some of them say false and others say true. And so let's look at the first one. The statement is false because the first 4 perfect numbers are 8, 28. Let's stop right there. 8 is not a perfect number, at least not the first one, because we already know 6 is perfect. So because we know 6 is perfect, we know that first one is out. That first one cannot be true. So it's not option A. Second one, the statement is true because the first 4 perfect numbers are 6, 28, 496, and 8128. The statement is true because the first 4 perfect numbers are 6, 28, 946, and 1828 is the next one. So we can see that there's some differences there. We'll be able to rule out, actually we saw 28 was perfect, and we saw that 26 by a question that we did was not perfect. So we can rule out C. So the answer really is B. I'm sorry, we could rule out D. The answer really is one of the middle two. So the only thing that they differ in, actually they differ in the 496 and the 946. So let's try 496. It's the smaller of the two. If 496 is perfect, then we know it's option B. If 496 is not perfect, then we know it's option C. So 496, this is why I thought it might be hard. I don't think we have to try the big numbers, because if we can tell a difference between 496 and 946, then we have it. So we know 1 goes in there, so I'm going to start listing them out. 1, comma, and definitely 2 goes in there. Let's look how many times 2 goes into 496. 2 goes into 496, 2, well, we can use a calculator, right? For time's sake. And oops, I hit division twice. So 496 divided by 2 is 248. So we have 2 and 248 is going to be our top one. Will 3 go in there? 4 plus 9 plus 6 is 19. 3 won't go in there. 4 into 496 will go, because the result of dividing it by 2 is even. So if we divide it by 4, we get 4 and 124. We know 5 doesn't go in there. 6 can't because 3 didn't. We've got to try 7, but we know 7 won't, because 7 will go in evenly to 49, have a remainder of 0, and won't go into 6. 8 into 496 will go. And the reason why we know that is because division by 4 was even. So 8 and 62. Okay, so we're getting closer. 9 won't go in because 3 didn't. 10 won't go in because 5 didn't. 11 we should try, in case it's divisible by a prime. Doesn't work. 12 can't go in because it has a 3. 13 we need to try. Doesn't work. 14 won't work because 7. 15 won't work because of 3. 16 might. Let's try 16. 496 divided by 16. And this is where it will get a little bit long. So we got a 16 and a 31. We've narrowed that gap a lot. 17 we'd have to try because it's prime. 18 can't go in because a 3's in 18. 19 we'd have to try. And as I try 19, it goes in 26 times potentially, but it's not even. 20 won't work because 5 doesn't. 21 won't work because 7 and 3 don't. 22 won't work because 11 didn't. 23 we'd have to try because it's prime. Doesn't work, but I've looped myself. When I look at division by 23, it says my number has to be under that. So these are our prime factors. I'm sorry, our proper factors, not prime. And so let me add them up. So we're going to take 1 plus 2 plus 4 plus 8 plus 16 plus 31 plus 62 plus 124 plus 248. And when we hit equals, guess what we get for the sum? I didn't know this. The sum is 496. It is perfect. And so because it's perfect, we know that we already found out that the first two are 6 and 28. We didn't know they were the first two, but this definitely tells us that there was nothing in between 6 and 28. And we now know 496 is perfect, which means it's option B. And we are done. So it could take a little bit of time with these questions, but there's not too many that have big numbers like that. So the next section of problems deals with what they call twin primes. So twin primes are numbers that, well, let me define them. So actually it's defined here. Prime number is prime numbers that are different by 2 are called twin primes. So let me fix that. Prime numbers, I don't know why that didn't come across, that are different by 2 are called twin primes. Some twin prime pairs are 3 and 5, 5 and 7, 11 and 13, and so on. There's something called the twin prime conjecture, that there's an infinitely many pairs of these primes, and what they found is they found a ton, but no one's been able to prove that there's been an infinite amount, that there definitely is. And so what they're going to ask us to do from time to time is um, something like this, the way that they get at this, they may ask you some true-false questions. But from a working standpoint, they saw this in the homework. Find the twin primes between 25 and 35. And they never pick anything too big because that would be very hard because they get spaced out a little bit later on. But there's some in between 25 and 35, or at least one pair. So let's start listing out the primes that are between there. We'd only consider odd numbers because all the even ones will be non-prime because they're divisible by 2. 27's not prime. 29 is. Whoops. 29 is. And the next prime number is 31. Oh, there's my twin primes. And you're done, just like that. So we're dealing with some twin prime types of ideas here. So that's it really with twin primes. I think most of your work will be in regards to this pretty straightforward. It, it finishes out with what's called, and it's on page 201 in the text. Actually, let me come down here. Not sure why it's putting this line in here, but I'm going to come down here. Page 201 in the text, in the 5.3, talks about what's called primordial primes. Now, the primordial number is denoted something like this: P with the hashtag next to it, or P with the number sign. And so the primordial primes are potentially generated by a primordial number plus or minus 1. So I need to define for you what a primordial number is. A primordial number is P1 times P2 times P3 ... times Pn. And what these P's are is the product of the first n primes plus 1. So the product of the first n primes plus 1. So P1 is always 2, P2 is always 3, P3 is always 5, then 7, and it would just keep going however many they want you to do. And if you multiply them together and add and subtract 1, it's a way that they were hunting for primes. And hunting for primes is a pretty big idea, especially in regards to some stuff that happens in what do you call it? Encryption, right? Encryption. The way that we encrypt is dealt with primes. So one of the questions that they asked, and in the homework about this, and this happens about problem 13, 14, or 15, is they say, so the primordial primes would take that P number and add and subtract 1. So this is a question that I saw in the homework. Which, or what, two numbers does the primordial formula So the primordial formula is the one that's boxed. Maybe I should call that formula. It doesn't necessarily generate a prime, but it often does. What two numbers does the primordial formula produce? 4p equals 7. So if we understand this formula right, and we do 7, the primordial number considered with 7 would be 2 times 3 times 5 times 7, not 9. The next primordial number, or next prime number, is 11. The next one's 13, and the next one is 17. Right? Am I thinking about that right? 2, 3, 5, 7, not 9, 11, 13, not 15, but 17. 1, 2, 3, 4, 5, 6, 7. We're going to do that product. It's going to be a big number often. Okay, so the product of that is 510, 510. Interesting. And we're going to add and subtract 1. Now, the reason why they add and subtract 1 is you're guaranteed to get an even number with the 2 in the mix. And so one of the numbers is 510,509, and the other is 510,511. And so, okay, it's not coming up with those when I do that formula. Okay. Oh, I'm misreading this. Okay. The first n primes plus 1. So this is not correct. When they say p hashtag, this p is a prime number. So I was wondering why I went to go enter it in and it's not anywhere close to what they're giving me as options. So I misdefined this for you, and I'm sorry about that. Maybe this is a good thing. This is the stopping point. So, for example, this Pn is P itself, right? So they put Pn, but evidently it's P itself. I was reading it in the book and it sounded a little bit different. Okay. So what do they really want here with P equal to 7? Not for you to get a huge number like that. And it makes sense to me because their next question is hard for us if the number is really big. So when they say 7 plus or minus 1, they want us to do 2 times 3 times 5 times 7 plus or minus 1. So that's way different. 2 times 3 times 5 times 7. So they're giving us a stopping point as opposed to the number of prime numbers. So now I have 210 plus or minus 1. And so my two options are 209 or 211. Right? Or those are not my choices. Those are the two that are created. And those are options for me here. Okay, now it wants to know if any of those are prime numbers. Now they may both be prime. I don't know. Actually, sorry, I wrote that wrong. 211. So I wrote that wrong. So how about these guys? Are they both prime, do you think? Is just one of them prime? And this is where it gets a little bit difficult. So we know 2 doesn't divide into the number, 3 doesn't, 5 doesn't, 7, 209 divided by 7 doesn't work. The next prime number, and so we'd have to kind of keep going up and trying different prime numbers. So 11, yeah, 11 does work. 11 times 19 is 209. So I'm really happy that happened because that's not a number that we would have recognized as divisible by 11. But I just found out by just trying the primes that 11 times 19 is 209. So 209 is not prime. 211? Maybe. We'll see. 2 doesn't work. 3 doesn't work, right? Yeah, sum of the digits is 4. 5 doesn't work. 7 into 211 doesn't work. So if I start making this my doesn't work, 11 going into 211 we know won't happen because it went into 209. 13. Now, when I tried by 13, I'm already a potential of 13 times 16 and some change. It's got to work out perfectly. So when I go to the next prime number, 211 divided by 17, it is 12.4. So I've fallen. So there's no need to keep checking. We've looped ourselves. So 211 is prime. So I would type in here the number 211 is prime and check that answer. And it would say, hey, you did a good job. So I'm looking at the homework right now. I did remember that there's one last thing in this section, this 5.3 section, and it's called the Goldberg. Actually, I don't know if it's Goldberg. Let me find the actual name. Gold box. That didn't sound quite right. Gold box conjecture. This is also not proved. So if they give you a true-false question, whether it's proved or not, it's not proved. And it says this: every even number can be written as a sum of two primes. So for example, if we took a number like 12, 12 can be written as, let's consider the prime numbers. The prime numbers are 2, 3, 5, 7, 11, and yeah, 5 and 7 add up to be 12. So it's the sum of two prime numbers, right? And they're saying that can happen for every even number. So this wouldn't be a conjecture if they ever found an example where that didn't happen. And so when they say they haven't proved it, they haven't proved it in general. They're watching it happen for all the even numbers, but they haven't been able to prove it, right? And I guess I should say this: every even number, there's an important part that's left out here: greater than 2. It doesn't work for 2. Okay, there is a number that we saw it wouldn't work for. And so let me pull up an example and write it down for you. So there's a few twin prime examples. Okay. So one of the questions is something like this: the equation 17 plus 51 equals 68 verifies Goldbach's conjecture. And then it's a simple true or false, right? And so that's one of the ones I'm seeing. What do you think? It verifies Goldbach's conjecture only if those two numbers are prime. They don't have to be successive primes like 5 and 7. Nothing was said about that. So 17 and 51, are they prime? 17 absolutely is. What do you know about 51? 51 is not prime. Why? Because 5 plus 1 is 6. So I know 3 goes into 51. Let's see how many times. 1. Sorry about that. 17 times 3 times 17 is 51. So it's not prime. So this is false. It would only verify it if the two numbers happen to be prime. So another Goldbach question is something like this. They're going to pick an even number, relatively small, write 36 as a sum of two primes. And they're not leaving you hanging. They're giving you some way to be led in that. So let me show you your answer choices. A, 36 is equal to 20 plus blank. B, 36 is equal to 17 plus blank. C, 36 is equal to 2 plus blank. And your job is to fill in the blank. So they're not leaving you like totally helpless in there where you're having to search for it. There is one that should be obviously ruled out right away. Do you see which one that is? The first one cannot be right because 20 is not prime. So that one's gone. So from a vision standpoint, all we have to look at is B or C. Once you rule out one, you'll know it's the other. So if we look at 36 minus 17 to see what that makeup is, well, that's 19. Well, 19's prime. Done. That's our guy right there. It's the sum of two primes. 36 is 2 plus. Well, we knew that would be 34. And 34 is not prime. So it's definitely B. So it's not like you're going to have to hunt through all the primes. I was surprised about that. But all questions related to that kind of lead you in this manner. So lots of kind of cool things about prime numbers are coming up in this section. We got twin primes, perfect numbers, abundant numbers, apologize about the misleading you on the primordial formula, right? But they're naming the stopping point. So whatever that p number is will be prime, and you stop at that prime and multiply all the primes previous to that and add and subtract 1. All right, have fun in 5-3.